Okay, so here we are. We're just at the critical moment. Okay, so what these equations imply, you string these together and we have u prime ct now is strictly greater than u prime et ct plus 1. But u prime is a downward sloping function. So this equation implies that et ct plus 1 is strictly greater than ct. So when we added this condition, we destroyed the random walk prediction of this, I'm sorry, the key. We destroyed the random walk implication. And we got the implication that consumption, it was true that the marginal utility of, it was still true that the marginal utility of consumption was a martingale, but consumption is what's called a submartingale. And this is an unbounded, in this case, this is an unbounded submartingale. And as we're going to see, there's something called a submartingale convergence theorem. And a submartingale convergence theorem, CT is going to diverge to plus infinity for almost all sample paths. So this is a striking thing, which this is our first encounter with something called precautionary savings. So we've killed the Friedman-Hall model by changing this utility function, and that's all we've changed here. Okay, which is rather remarkable. So what we're going to spend the rest of today talking about is diving down into this. It turns out that this remarkable proposition doesn't actually need this. We can weaken this quite a bit, and people have weakened it. And the reason we're going to talk about this is the precautionary savings model and the precautionary savings motive is the foundation for much of things that are going to be studied in Professor Bohr's class, for example, where we talk about incomplete markets models later in the year. So that's going to be our break here. And now what I'm going to do is I'm going to go to chapter, start talking about chapter 18 of RMT5. And this is called self-insurance. And in some ways you can think about this as a follow-up to the little chapter on Ricardian equivalence that we talked about, that I asked you to read. And we'll talk more about this, because a lot hinges on borrowing constraints. And two types of borrowing constraints, so-called natural those are sort of the weakest. And what are also called ad hoc. I think Rao Ayagari coined this term. And these are tighter than the natural ones. Okay, so that's where this is coming from. So this chapter 18 is Lars Lundquist and my attempt to walk through sort of the heart of this classic paper by Chamberlain and Wilson. It's a 2000 paper that actually, this paper has quite a history. This paper was unpublished for, so I'll tell you a story about it. It was unpublished for, I think, at least 20 years. And it was a classic unpublished paper, and it had the key results. Now, why hadn't it been published? Well, Chamberlain and Wilson were both giants. Wilson was at NYU for a long time. I think they wrote this paper together when they were at Wisconsin. Okay, so they wrote this paper, and they got what they got was the result. They got the result that consumption diverges to plus infinity in a model that's slight generalization of the one we were just talking about, but did not assume, it did not assume anything about, it assumed that consumption was non-negative. And it assumed that it only assumed that marginal utilities of consumption were positive everywhere. Okay. It assumed not positive marginal utilities of consumption. And they got this result. So the referees, and the way they got the result was submartingale convergence theorem. That played a key role. And the way the referees said, okay, we see the theorem, we see how you proved it, but there's no intuition. Tell us the intuition. And they struggled for years to satisfy the referee. And at one point they said, we really can't do it. The submartingale convergence theorem is going to have to speak for itself. The reason I tell you this story is that what's going on here is subtle, and these are great economists, and if they struggle with the intuition, don't be surprised if I'm going to struggle with it. Okay, so let me lay out their environment. So the environment that we're going to talk about when we do the formal stuff is going to be the following. There's going to be it's going to be quite simpler. There's going to be a person that cares about this kind of standard thing. Beta is going to be here. There's going to be a single good. Person is going to have an exogenous endowment, and we're going to make it very simple. We're going to have an ID, and it's going to live in some space, these possible values. This is the possible values. We're going to make it discrete. We're going to put probabilities pi sub s. That's equal to the probability that yt in any date is equal to y sub s bar. I'm going to do that. The pi s's are all going to be, they're going to be probabilities, and they're going to sum to 1. There's going to be no insurance markets. Instead, and I'm gonna follow. I'm gonna use sort of a trick that Rao Ayagari used in a famous paper that is going to be talked a lot about in the fourth quarter. I'm going to rewrite. Well, I'll show you what the. This is going to be the same as chapter 3 that we wrote. This person is going to have. And I'm now going to impose that CT has to be positive, non-negative. So there's going to be an ANATA condition or a restriction that CT has to be positive. Notice not true in chapter 3, Hall model. That was not true. Okay. Okay, so for this, to pursue an exercise in finding the state as an art, Rao Ayagari rewrote this. So rewrite this equation as could rewrite this equation just using a little algebra. Equals R. We're going to assume, following much of Chamberlain-Wilson, R beta is equal to 1. We're going to rewrite this equation as yt minus bt minus ct. And we're going to define, this was Rao did this to Bellmanize something more easily. He's going to reduce this dimension of the space. So if you ask why he did this, the answer is going to be he wanted to Bellmanize something easily. So we're going to define yt plus 1 minus bt plus 1 is equal to at plus 1. And what this is these are the assets a person has at the beginning of t plus 1 after yt plus 1 has arrived. That's what this is, okay? So what I can then do is I can take this equation and I could rewrite it as yt plus 1 minus bt plus 1 is equal to R. Well, it's equal to yt plus 1 plus R yt minus bt minus ct. And then I could just rewrite it as at plus 1. That's what this is equal to yt plus 1 plus R at minus ct. And that's how Rao Ayagari and we in this today, for part of today, sometimes we will write the time t budget constraint like this, and our constraint on consumption will be this. This is going to be convenient for us to do. So your consumption has to be positive, non-negative, and it cannot exceed the free assets that you have. And this is the okay. That's what we're going to study later. So we'll talk about this sometimes. And this CT being a positive, as we said, that's either an exogenous restriction or we're going to get it from an anomic condition. One of those two ways. Okay. So the restriction that we're going to impose in the Chamberlain-Wilson, we're going to impose this, and we're not going to write down a Bellman equation of that's associated with a consumer that wants to maximize. Our consumer wants to maximize the conditional expectation of this, subject to a sequence of equations like this, for t greater than or equal to 0. And we will start things off with a particular A0. So we will set A0 equal to Y0, and that's equivalent to setting B0, initial debt, equal to 0. So the Bellman equation for this problem is going to look like this. The optimum value is going to choose a maximum of consumption, and that's beta. Summation, our state goes from 1 to S, pi S V, and then this is going to be equal to R A minus C plus YS. Where that's our possible realization. So this value function V will, I want to say this, it's going to look like U. It's going to be increasing. It's going to be strictly concave. And it's going to be differentiable. And we're going to use that. Okay, so what we're going to do is we're going to study the solution of this. We're going to study this Bellman equation. Okay, so what we're going to do now is we're going to take a detour. Or is it a detour? Because it's going to, I think it's going to help us understand something. We're going to study a non-stochastic endowment. Study the same problem with a non-stochastic endowment. And our instincts are that this is going to give us a hint, insights about the nature of the solution with the stochastic endowment. That's where we're going. So I'm going to return to this. I'm going to return to the chapter 3 notation. So it's kind of, here's a hint. Could ask, why do we have two kinds of notation? This is kind of finding the state as an art. If I use chapter 3 notation here, I would have two state variables. And I would actually have two state variables here. And in the IID case, what Rao Aigari saw was that we could just have one state variable if we used his notation with these free assets. So I want you to think about that. Okay, so what I'm going to do is I'm going to replace, I'm going to use this. It's going to be exactly the same model, except the YT sequence is going to be an exogenous sequence. Here we have our sequence of budget constraints. YT is now, BT is debt, minus BT is assets. I'm going to express the a no borrowing constraint What does that look like? A no borrowing constraint could look like, it could look like this. That assets have to be, or BT plus 1 is less than or equal to 0. That is, so we're going to impose this. You can issue no debt. Or that this is the same as saying that your assets have to be non-negative. We're going to impose a no borrowing constraint now, and we're going to study it. That's what a no borrowing constraint is, if we impose a no borrowing constraint. A natural borrowing constraint is something different. That would say that your debt, it actually could be positive. What could it be in the spirit of chapter 9? Well, it could be your continuation non-financial wealth. This is your continuation non-financial wealth. And we'll call this thing BT bar. So what we're going to do is we're going to solve the consumer's problem under both a no borrowing constraint and under the natural borrowing constraint. And we're going to compare them. That's all we're going to do. So under the natural borrowing constraint, this has lots of the flavor of a baby's version of some things we talked about in chapter 9. Under the natural borrowing limit, the sequence of budget constraints can be solved forward to get a single budget constraint, a single intertemporal budget constraint. This is under the natural borrowing limit. This is, you could think of this sort of as if we've done this Arrow de Blue style, and that's a time zero budget constraint on a sequence, on sequences. So under the natural borrowing limit, that's the only restriction. So if we go get the first order necessary conditions for our problem, and the way I'm going to think about it is I could write the first order necessary conditions as follows. Actually, what I want to do is I want to oppose the restrictions like, it's like I'm going to put a Lagrangian, I think, rather than what's in the text, I would put a sequence of Lagrangians here on this, on these BTs. And then I would discover that first order conditions would look like this. And if they're equal, if BT plus 1 is strictly less than BT plus 1 bar at T greater than or equal to 0. So what you can check is it's possible to satisfy these at equality with a CT equals C bar, complete consumption smoothing for all T, where C bar satisfies this. So under the natural borrowing limit, complete consumption smoothing is possible. Complete consumption smoothing across states. That's possible. And that would be the outcome. And we could compute what BT would be, and we could verify that it would satisfy BT, that it would satisfy the borrowing, the natural borrowing constraints. This would be and this would be less than the borrowing constraint that we computed, the natural borrowing limit, the sequence of natural borrowing limits that we computed here. So this all fits together. Okay. So now we get complete smoothing. Now what we're going to do is we're going to add an ad hoc borrowing limit. And it's going to be in the form of non-negative assets. So we're going to impose the restriction that that R BT plus 1, R inverse BT plus 1 is their debt has to be negative, non-positive for all t greater than or equal to 0. You cannot borrow. You can only hold assets. And we're going to transform and work now in terms of, because it's going to ease a result, we're going to let AT equal minus BT plus YT. Go to this free assets definition. And we're going to let CT, AT, so now we're going to resolve the problem with these ad hoc borrowing limits. So this is an ad hoc, no borrowing. So we've severely tightened the borrowing limit, none at all. So we're going to let CT star, AT star be an optimum. And an optimum plan is going to have to, it's going to satisfy these conditions now. So we get our Euler equation. This looks just like we had in chapter 3. Not a surprise. Equals if CT star is strictly less than AT star. So if you're not at a corner, consuming all of your free assets, then you've got equality for any t. So along an optimum path, for t greater than or equal to 1, so this implies that along a path for t greater than or equal to 1, either something has to be true, either AT, CT minus 1 star is equal to CT star. So we've got temporary smoothing, or condition B, CT minus 1 star is less than CT star So consumption is actually rising, and CT minus 1 star was equal to AT minus 1 star, and therefore AT star is equal to YT. So look at this carefully. This is, you're off the corner. Write it this way. Here we're off the corner. And here we're on the corner. And when we're on the corner, there's two consequences. Last period, you consumed all your free assets. You consumed all your free assets that you had at that time. And at the beginning, as a consequence, you did no saving. You did no saving. And your beginning of period assets this period were equal to just your current endowment. So these are what our first order conditions are. And we see right away that with the ad hoc no borrowing limit, we don't get consumption smoothing, but CT star is a monotonically increasing sequence. Okay. So that's we get this directly out of the Kuhn-Tucker conditions for our problem. So I want to pause now. So all we did is we imposed the no borrowing limit. And we've got this monotone increasing sequence. Now, from a little bit of math that I remember, there's something called the monotone convergence theorem. So okay, there's something called the monotone convergence theorem, and what it asserts is that a bounded monotone sequence converges. And we've set this up so that this CT star, because of feasibility restrictions, they're going to imply that this is a bounded sequence. There's a bound on what consumption can be. This is connected with the way we've set this up with beta R equal 1 and so on. So what this implies is that under the set of coherent assumptions that we made, if the consumption process is bounded, it will converge here. Okay, so I'm going to come back, if I remember, the submartingale convergence theorem. Some people over coffee or beer would say it's kind of a stochastic version of a monotone convergence theorem. It's an exotic stochastic version of a monotone convergence theorem. So that's going to appear later. So there's some intuition there. Okay, that was a little bit of a detour. So taking these results A and B, we can do the following. We can solve the budget constraint of the forward. It's a difference equation. Solve it forward. To get the following. This is going to be the continuation. This is the continuation present value of consumption. This is going to be a pretty formula. There's your free assets. And that's the continuation non-financial wealth. So that what this says is that so sometimes an AT is greater than or equal to 0. So what we'll notice at dates t greater or equal to 1, for which AT equals YT, that means, what does that mean? No borrowing constraint binding. This equation becomes just by substitution. So this is binding. Now this is always. So these two equations give us lots of information. So what they say is when no borrowing is not binding, we are sort of in a temporary consumption smoothing. But when it becomes binding, when it becomes binding, the date when it becomes binding, when it binds, CT star jumps up permanently. So it says dates when it's not, when it's binding that you can't consume. You can't smooth the consumption. So, and now if the no borrowing constraint binds only finitely often, that means there's going to be a last date when it's binding. We're going to let t minus 1 bar be the last date it was binding. Then for t greater or equal to t bar, we have Ct is equal to C bar, where C bar 1 minus beta is equal to that's our formula. But until then, well, that's the way this fits together. And if we stare at these formulas, I'm just going to write down this thing. Xt is equal to, if I could rearrange this formula, to be C bar is equal to, so this is the way people do this. I've been using beta R equals 1. R, if I define R is equal to 1 plus R, where that's the net interest rate. And this whole thing is the gross. I could rearrange that equation above to be C bar is equal to little r over 1 plus R, summation J equals T to infinity 1 plus R to the T minus J yj. Where this would be T bar. That would be T bar, and that would be T bar. I could rearrange that. So let's just define this. Because this is a number that's going to be useful to us. I'll just kind of define the generalization of that. This is the continuation. This piece is the continuation present value of the endowment. And this thing is just an interest rate factor. It's an annuity factor. It's an annuity payment. It's an annuity ratio. It's if I had that much wealth and I annuitized it, how much could I get every year, every period? And that's the answer. So I'm just going to take now the annuitized value more generally, like this. And what this thing is, this is the annuitized value of continuation non-financial wealth. Okay. So here's a proposition, which we virtually, we've got all the ingredients for proving it. I'm not going to prove it. So given a no borrowing constraint, that C bar is equal to the limit as t goes to infinity of our plan. It's equal to the supremum, the biggest value of xt, which is equal to x bar, where this is xt. So what's happening, sketch of what's going on here is, if we wrote down what's going to be happening, here's time, here's consumption. In this model, what consumption is going to do is it's going to take these jumps. And it's going to jump, CT jumps, when the no borrowing constraint binds. Okay, that's how this machinery goes.